Hello, welcome to this video produced as part of the Further Maths Support Programme as material for A-Level Maths and Further Maths. This one focuses on the basic principles of impulse and momentum. It's section 1 and the first part is about momentum, its definition and its calculation. We're going to talk about collisions. That's why we need momentum, though the reason for it will not be apparent in this video. We're interested in the definition here, and the definition is that momentum for a body is its mass times its velocity. Mass is a scalar, velocity is necessarily a vector quantity, so when you multiply the two you will get a further vector. So momentum is indeed a vector quantity and its units are Newton seconds. Now for a moment it won't be apparent why we get to that. It's simply that if you measure mass in kilograms, velocity in meters per second, that's the unit you end up with, but the explanation for that will come later. Now often we need to work out a change in momentum, and so that will simply be the final minus the initial momentum. And the other thing to watch out for is that momentum is not a measure of energy. For a start it's a vector, not a scalar, but the two concepts simply are not the same. Let's look at a first example, the magnitude of the momentum of two different bodies. A speedboat of mass 180 kilograms moving at 80 meters per second, and a steamroller of mass 3.6 tons moving much more slowly at 4 meters per second. Now the definition is momentum is mass times velocity, so in the first case it's just going to be 180 times 80 and the unit will be Newton seconds. The second we need to change the tons to kilograms, so it will be 3,600 times 4 and again Newton seconds. So working out the two, we get for the first one the calculation works out at 14,400 Newton seconds, and for the second it's the same, interestingly, though coming from different numbers. Now here's the point to notice that momentum and energy are not the same, because if we were to work out the energy of the boat, it will be half times the mass times 80 squared. And if we were to work out the energy of the steamroller, it would be half times 3,600 times 4 squared. Well, if you think about 14,400, that's come from having no half and only 180. So when you work out the energy, it's going to be 40 times as big as that number. Look on the other hand at this one, you got no half and you've only got 1/4, so the difference will be half times 4 times what you had before. You're only multiplying that by 2. So the figures for the energy will be quite different for those two, even though the momentums are equal. But it's quite spurious to think that the energies would be equal. It's quite specious, I should say, to think that the energies would be equal, because one is a vector quantity and the other is momentum is a vector quantity and energy is a scalar. So there's just no reason why they should be the same. So we have the same momentum but not the same kinetic energy. Now we want to find the change in momentum of a body of mass 3 kilograms when speed increases from 6 to 15 meters per second. It helps to have a way of representing this in a diagram. So here we go. You draw a picture of the body and you put above the situation beforehand and below the situation afterwards. So in this case we can see that the initial momentum will be 3 times 6, and that will be Newton seconds, and afterwards it will be 3 times 15, again Newton seconds. So we end up with a change in momentum, subtracting one from the other, of 27, and it is a matter of saying 45 minus 18 because both those momentums will be directed to the right. So we really have another vector showing on the diagram, which is the momentum. Let's show it with an open arrow so that it's not the same, and that will be 18 in this case and it will be 45 in this case. Now find the change in the body of a mass 3 kilograms when it changes from 5 meters per second one way to 4 meters the other way. Now, it's a similar kind of diagram, but this time we need to be careful about signs, because although it's obviously 15, it's going to be plus 15, taking positive to the right. And in the other case, it's going to be minus 12. So this time the difference is not 3, but 27. And the difference, now we've got to be careful about signs. So let's see what happens. We're going to end up with minus 27 because it's the final minus the initial. So that's minus 12 minus 15 is minus 27, and that's with respect to taking positive to the right. Now, that's implied by having well, it isn't really implied. You should make that clear on the diagram. What we're saying here is that our positive direction is in the same direction as the 5 meters per second. So you could give this answer as saying that the change in momentum is 27 newton seconds in a direction opposite to the original 5 meter per second velocity. That would be another way of expressing it. But it is important to have a sense here of just what is meant by direction, since it's a vector quantity. Well, that ends this video presentation on momentum. The next in the same series on impulse and momentum, section 1, focuses on impulse. I hope to be with you later to explore that.